Well, now we're going to take a look at a rather lengthy theorem, and I am not going to prove it. As a matter of fact, one of these, or one or two of them, you'll probably have to prove for your homework, but I will prove maybe a portion of one of them. Here's how the statement goes. F is a function from A into B, and then we got a bunch of subsets of A. We have P1, P2, and this is a whole collection of them because alpha is in an index set I. So if the index set were the, I don't want to say natural numbers, but natural numbers 3 or greater, then this would be an infinite number of sets. This would be P3, P4, P5, dot, dot, dot. So again, P alpha is the index set. Alpha is an element of the index set. So it's possible this is just one set or a finite number of sets, but it could also be an infinite number of sets, and it won't matter for us. First one says that if P1, remember they're all subsets of A, all of these P sets. If P1 is a subset of P2, then the image of P1 is a subset of the image of P2. That would be a very simple proof, but let's just maybe draw a picture. If we have, let's say this set is P2, and inside it is P1. Well, if the image of P2 under F is something like this, I'll make it look like it's the real image there. Okay, so if F of P2 gives you all of this, that's F of P2. Well, P1 is completely contained inside P2. So therefore, its image can't take you anywhere outside of this. So it's going to be somewhere, inside of that. So that's a messy image that kind of describes what this statement is saying. P1 is a subset of P2 means that the image of P1 is a subset of the image of P2. And for some of these, it might be worth your drawing pictures if we don't go through the proof, just to make sure you understand what it's saying. B says that if you take the image of the union of all of those PI sets, this could be an infinite number of them. If you take the union of all of them and look at the image, that's going to be exactly equal to if you were to take F, the image of all of the individual sets, and union them together. That one takes a little bit of thinking, and it wouldn't be a very difficult proof. The third one says that it's similar to the part B. This is part C. If you take the image of the intersection of all of those P alpha sets, could be infinitely many, the elements that are in every one of the sets, and take the image of that set, it's going to be equal to, if you were to take the intersection of the images of all of the individual sets. D is not an equality, but it's a subset. The image of P1 minus the image of P2 is a subset of the image of P1 minus P2. Remember what that is? P1, it's set subtraction, set difference. P1 minus P2 is take all the elements of P and then remove every element from that set that is in P2. E, this is an interesting one. F is injective. It's 1-to-1. If and only if the image of the intersection of P1 and P2 is equal to the image of P1 intersected with the image of P2. And that would have to be true for all P1 and P2, any two subsets. Then the final one, F is injective. If and only if the set difference, the image of P1 minus the image of P2, is equal to the image of P1 minus P2. Okay, we're just going to prove maybe one direction of E. F is 1 to 1 if and only if the image of P1 intersect P2 is equal to the image of P1 intersected with the image of P2. Okay, so we're going to do the standard way of proving two sets are equal. We're going to show that we're going to assume this is true. Let's see. Yeah, we're going to, for the first direction, we're going to assume this is true, and then we're going to prove that this is true. In proving this is true, when we're going, if we go this direction, we get this kind of for free by C, which we didn't prove, but this P alpha could just be two sets. This says that F of P1 intersected with P2 is equal to the intersection of the two images of the sets. So we get that direction for free. Now let's look at the backwards direction. For the backwards direction, I guess I should have put, we're doing this part first. And this, we're assuming this is true. And in order to prove that this set is equal to this one, I have to show this is a subset of this, and this is a subset of that. So under this main one of the two directions, I don't think I'm going to have enough room to prove the other direction, but to prove this part, again, we're assuming F is injective, prove this is true. Well, that subset that way we get for free using part C. Now we're going to go this direction. We're going to prove this is a subset of this, which means take an arbitrary element of this and prove that it's in this. So let B be an element of this. To show, that's telling the reader what we're going to do, to show that B is an element of this. And I lost my black pen, so I'm going to change colors here. So let B be an element of the right-hand side to show that it's an element of the left-hand side. Okay, well, if this is true, then by definition, I'm not going to put of intersection, but by definition of intersection, what that means is that B is an element of F of P1, and F is an element, B is an element of F of P2. Okay? What does it mean for B to be an element of F of P1? That means that there is an A1 that gets mapped to B, an A1 in P1. And there's an A2, a different number in P2, that gets mapped to B as well. Okay, so I can say by definition again, only this time it's by definition of the image of a set. If B is an element of the image of P1, there exists an A1 such that, and A1 would be in A, in capital A, such that A1 is, F of A1 is equal to B. I'll write it like B equal to F of A1. And likewise, and there exists an A2 in A such that B is equal to F of A2. Okay, but F is 1-to-1 injective. So if B is equal to F of A1 and F of A2, that means that A1 and A2 are the same number because F is 1-to-1. You can't have two different numbers, A1 and A2, both mapping to B if it's a 1-to-1 function. So F is 1-to-1, so A1 is equal to A2. they're equal. Thus, B equals f of A1. Let's see. Oh, that means that A1, since A1 is equal to A2, A1, let's see, they would both have to be in, I'm sorry, A1 would have to be in both of the sets. So, thus, A1, we already knew that A1 was an element of P2. Actually, I made a mistake here, sorry. A1 is in P1, A2 is in P2. Sorry about that. That's what this means. It means there's an A1 in P1 such that f of A1 gives you a B, and A2 would be in P2, which means f of A2 gives you a B. Thus, A is in P1, but A1 is equal to P2, so it's also in P2. So A1 is an element of the intersection, which means it's in both of those sets. So, which implies B, which is equal to f of A1, is an element of f of P1 intersected with P2. That's exactly what we needed to prove. That's because A1 is in this set. It's in both P1 and P2, and B is equal to that. So we did this, and I'm just going to say that I ran out of room. This is a problem for the student. It's not too difficult. As a matter of fact, I'll tell you how to do it. Use contrapositive. For this.